Okay, so let's get started. So welcome to the joint astronomy colloquium of today. We have a local, one of us, so to say, speaking today, Friedrich Roepke. So many of you know him, so I don't think we need a very long introduction, but the introduction will be even if a short one. So Fritz did his studies in Jena, also spent during his studies a year in Virginia, USA, and then did his PhD at the Max Planck Institute for Astrophysics in Garching, where actually the two of us overlapped, so we know from that time. And in 2003 he did his doctoral degree there. Then he spent a couple of more years there and then went for a postdoctoral position in Santa Cruz. And after that became a Eminota research group leader, again in Garching. And then started in 2011 a professorship in Würzburg. And we were lucky that we could lure him to Heidelberg here at the Center for Astronomy, joint appointment between the university and the Heidelberg Institute for Theoretical Studies, HITS, where he is currently a full professor. So he's working on very fascinating simulations of stars in their last final moments, and so I'm looking very much forward to his talk. And so he will talk about the 3D view in stellar astrophysics, on a lot of stuff that's been done in his group at HITS. And so let's give him a warm round of welcome.
All right, thank you very much. So, as Kees already said, since this is kind of a local colloquium today, I thought I would take the opportunity to give you a rather broad overview of what we really do in our Physics of Stellar Objects group here at the university, but also on the other side of the river at the Heidelberg Institute for Theoretical Studies. Since Heidelberg astronomy community is rather scattered over the city, it's sometimes actually good to give an overview of actually what is done in these different groups, and this is what I'm trying to do today. So I will not go much into depth about the different topics that I'm going to cover, but I actually want to show you what different processes in stars and different objects we are interested in. So we basically do everything under the common theme of 3D or hydrodynamical modeling of stellar objects. So this actually sets the scale in the astrophysical different scales that you can imagine that we are interested in. So it's stars, stellar objects that we try to model. And of course, this is a larger effort and many people are involved in this. So this is our group at the Heidelberg Institute for Theoretical Studies, but also a large number of external collaborators are involved in this. And I actually was lucky that one of our collaborators gave a colloquium only 2 weeks ago, Raphael Hirschi from Kiel University, and he already gave all the introduction that I could only repeat now of why we are interested in stars. So I will make this very short, just mentioning, of course, that stars are the fundamental building blocks of the universe. Stars make the universe. Observables are the classical targets of astronomy and are involved in a large number of processes that are actually important for different scales in astrophysical processes. So in the background you see the cosmic cycle of matter, where stars actually enrich galaxies with heavy elements. Now, I will more focus here on discussing why actually modeling stars is rather challenging, and as quite often in astrophysics in stellar modeling we encounter the common problems, namely a multi-physics challenge. So in stellar objects, of course, many different physical processes are at play at the same time. And then we also encounter a scale problem, as in many other astrophysical objects. And as usual, we have a spatial scale problem, we have a time scale problem, we actually have a wide range of densities, and this maybe is a bit particular to stellar hydrodynamics. We also have a velocity scale problem, and I will actually talk about this in a bit more detail later on. Now let's first look into the spatial scale problem. Well, of course, this arises from the fact that we are interested in modeling macroscopic large objects, stellar objects, in which the physical processes are quite often governed by microphysical effects on small scales. So therefore, it is usually the approach to take effective theories to describe such macroscopic objects, and we do that as well using the concepts of thermodynamics and fluid dynamics to describe stars. Now this is basically the set of equations that actually allows us to model stellar structure and stellar evolution. It's all based on stellar fluid dynamics. And of course, these are the familiar equations, the Euler equations of mass conservation, momentum balance, and energy balance. Now what we need in addition in stars is, of course, there are reactions going on, nuclear reactions, so therefore we need an additional set of equations that accounts for species balance. Now, the physics actually then enters, that's specific to stars, through the source terms. Of course, stars are held together by self-gravity, so these are the gravitational source terms. In the most general approach, they could be obtained from solving the Poisson equation. And then, of course, we need to take into account also species, changes in abundances of species, and energy generation by nuclear reactions. And this is usually done with an extended, more or less extended nuclear reaction network. To close this system of equations, we need an equation of state where a number of microphysical processes is then entering, and of course you're probably familiar with the effects that we have to take into account here. Now all this set of equations that's shown here on that slide is actually only the very fundamental and basic set of equations that one could use. Of course, there are many other physical effects that can be taken into account for stellar structure and stellar evolution. So this then would require to introduce more terms into these equations to then also account for things like conduction, radiation, magnetic fields, and so on. Now, this set of equations in principle is, from the mathematical point of view, rather complex. We can solve such equations with big computers nowadays, but of course this was not the case in the early 20th century when people started to model stellar structure and stellar evolution. So therefore, these early models made a number of assumptions, namely, first of all, and most prominent, the assumption of spherical symmetry, which reduced the problem to essentially being one-dimensional. And of course, this made the computations then much easier. The other approximation that was made is that stars were actually assumed to be always in hydrostatic equilibrium. That actually helps with the temporal scale problem. And then in the most simplistic stellar models, of course, binarity, magnetic fields, and other complications were also not considered. So this is basically how a star looked in the 20th century. And of course, we know that nowadays with modern observations, we know that stars actually look a bit different. So we actually see 3D structure in stars. So structures are not necessarily spherically symmetric. Stars are not always in hydrostatic equilibrium. Of course, the most prominent example for that is then the end stages of stellar evolution and supernova explosions, where we diverge strongly from hydrostatic equilibrium. We know that many stars come in multiples, especially massive stars, and binarity is a very common feature of stars. And of course, already from our sun, we know that many stars actually also feature strong magnetic fields. Nonetheless, it's quite impressive that despite all these simplifications and approximations that were made in early stellar theory, this theory was very successful in explaining the structure and the evolution of stars over a rather wide range of masses. And this theory could provide at least a qualitative understanding of stellar evolution and also make some qualitative predictions of the fate of certain stars. So this actually is quite a success, and I find it still rather remarkable that actually with these strong simplifications all this was possible. However, all this came at a price, and the price was that actually to include all the required underlying physics into this simple one-dimensional classical theory, parametrization was necessary. And these tunable parameters that were introduced here actually led to models that in the end have rather little predictive power, and therefore especially quantitative predictions of how stars would evolve are still difficult with these kind of models. However, the advantage if you have tunable parameters in 1D models is always that you can fit observations rather well. And this actually is still quite successful with stellar models, although in the era of precision stellar spectroscopy and astroseismology, these models now come more and more into conflict with the observational constraints. So therefore, a goal would be to develop now a new generation of stars, the stars of the 21st century, that would be based on dynamical and multidimensional models of stellar structure, evolution, and explosions. So this is actually what we are aiming at. And of course, this is a long way to go, but of course, one has to start somewhere. And the first step that we would like to take is, of course, to just abolish the simplification of spherical symmetry. Now this, of course, is easily done if you think back of the equations that I've shown. They actually were written down there in principle in multi-D, so you can actually solve these equations provided that you have enough computational power. And I would argue that actually computational power nowadays is sufficient to deal with these problems. And Raphael Hirschi in his colloquium 2 weeks ago demonstrated how multidimensional flows in stars can be simulated. But it is not only sheer computational power that is required to develop the next generation of stellar models, but also we need new modeling approaches and new numerical methods. And this is actually what I will focus here mainly on in today's colloquium talk. And I will actually give you 3 examples of where we need to develop new models, and new numerical approaches are helpful to address problems in stellar astrophysics that could not be actually covered consistently in 1D parametrizations. And the first example is convection in stellar interiors. Now here we remove the simplifications of spherical symmetry and that of hydrostatic equilibrium, although for the time being we do not diverge very much from hydrostatic equilibrium overall. The stars are still very close to hydrostatic equilibrium. Only in some radial zones we diverge from this, and then convective motions arise. But we still actually keep the simplifications of leaving out binarity, magnetic fields, and other complications. Now, in addition to the spatial scale problem, what we encounter in this case is a strong timescale problem. And this timescale problem, of course, derives from the very way we actually model stellar structure and stellar evolution. You've seen these equations before, and they involve a number of timescales. So one timescale that you learned about probably in your stellar structure and evolution course already is the timescale on which a star reacts to a perturbation of its mechanical equilibrium. This is the dynamical timescale, close to hydrostatic equilibrium, equivalent to the freefall timescale. And for the Sun, this is actually on the order of 27 minutes. Now, the reaction of a star to a perturbation of its thermal structure happens on much longer timescales. The Kelvin-Helmholtz timescale that can be derived from the Virchow theorem, for instance. And for the Sun, one then finds something like 20 million years. And another timescale is actually introduced by the source terms, accounting for nuclear reactions, because they actually involve the nuclear reaction rates. And from that, the nuclear timescale derives, and it can be very long for hydrogen burning in low-mass main sequence stars, as our Sun. It can be hundreds of gigayears. So that means that the timescales involved in this problem in modeling stars cover something like 15 orders of magnitude or something like that. Now the problem with this is, if we discretize the equations that I've shown before in a straightforward, traditional, explicit in time way, then in order to solve them numerically, there is a constraint for stability of numerical schemes, and this is this well-known CFL condition, which actually means that we have to follow the evolution of that stellar object on the smallest possible time scale here, namely roughly on the dynamical time scale, or more precisely on the time scale of sound crossing over a computational grid cell. So that means that we actually would need many, many time steps to cover the evolution of stars. And in particular, if one thinks about convection in stars, which Raphael Hirschy talked about, then the Mach numbers are pretty low. And suppose you have a flow that has a Mach number of, say, 10 to minus 4, which could be typical for stellar convection, then this means that we have to take 10,000 time steps to move one fluid element from one grid cell to the next. So therefore, explicit time discretization is very inefficient in this approach. Now this is obvious from going back to these equations, the homogeneous Euler equations for the moment. So here I removed all the source terms for simplicity, and then this set of equations can be rewritten in a more compact notation so that we arrive at this system of PDEs in this compact notation, where the time derivative of the state vector that involves all the conserved quantities, then plus the divergence of the fluxes of these conserved quantities is equal to 0. Now, suppose that we have devised a way of how to discretize the conserved quantities in space. So that's the spatial discretization of the state vector u, I, j, k in the 3 spatial dimensions. Now, we want to actually find a way to actually discretize this equation that results from a spatial discretization now also in time. So that means that we have to replace this derivative here by a numerical approximation. The way this is usually done is that one replaces this derivative with a finite difference, like here. So this is a simple forward Euler discretization, where this time derivative is replaced by the state vector evaluated at the new time step. This is hard to read here. It should read u n plus 1, meaning u at the new time step n plus 1 minus u at the old time step n divided by our time step delta t. And then we have the other term, the flux of divergence of the fluxes of the conserved quantities, called the residual here. And this residual can be evaluated, for instance, at the old time step un, because we know what the conserved quantities there are. Now this actually is explicit time discretization. And if one does the stability analysis of such schemes, one finds that this discretization is only conditionally stable. And the requirement for stability is what I referred to already, the CFL condition. So we have to take time steps that are smaller than the fastest signal speed, hydrodynamic signal speed, over a grid cell, so roughly faster than the sound crossing time over a grid cell. Now there's an alternative way of discretizing such equations, and this is the implicit time discretization. So here, instead of evaluating the residual at the old time step n, we now evaluate the residual at the new time step n plus 1. And this actually can be shown, this tiny change in the discretization has a huge impact on the stability of the scheme. It can be shown that then one arrives at a scheme that is unconditionally stable. So such schemes can take arbitrarily long time steps in principle without losing stability. Now this doesn't mean that the computation becomes very accurate. We still have to resolve the physical processes we are interested in, but instead of following, say, a flow that has a Mach number 10 to minus 4 on the sound crossing timescale, we can actually now follow it on its physical timescale and then maybe move one fluid element from one cell to the next in only one time step, saving a factor of 10,000 or so in the time steps for Mach number 10 to minus 4. So this is a huge advantage. However, there's no free lunch, and this comes at a price. And the price to pay is that we have to solve this large system of equations, then this implicit system of equations, and this is computationally very expensive. So therefore, there's always the question, when is it actually advisable to use implicit time discretization? When is that better than explicit time discretization? And the answer to that question depends on the problem at hand and also on the way of how you solve the system of equations. But what one usually finds is that Mach numbers that are below, say, 10 to the minus 1, 10 to the minus 2, it becomes more efficient to use implicit time stepping. Now this, therefore, was implemented into our stellar hydrodynamics code that was actually written in large parts by my former PhD student Fabian Mitschek, and we call this the 7-league hydro code, referring to a fairy tale theme of magic 7-league boots that allow you to take large strides of 7 miles each. And this, of course, refers to our long time steps that we can take. While later on we discovered that this was perhaps a bad choice because this is actually known in French, it's known in German, it's known in Swedish, it's known in Spanish, I think, but it's not known in English. And so therefore, maybe this was an unlucky choice, but we still thought that this actually characterizes our code rather well. So this code actually features implicit and explicit time discretization, so we can actually, in principle, now follow the evolution of low-Mach number flows with an appropriate time stepping. But this is only one part of the story. Because, as I mentioned already before, what we also encounter here is a velocity scale problem. And the velocity scale problem, again, arises from the low Mach numbers that we usually find in flows in stellar interiors. The question that arises here is, do traditional conventional hydro schemes, are they able to recover low Mach number flows? And we have tested this, and this simple test here shows a rotating vortex, the so-called Gresham vortex, that should happily turn around and rotate when you set it up. It should be a stable solution. And we have tested this with a conventional hydro scheme here. When it rotates with a Mach number of 10 to the minus 1. And what the picture here shows is this vortex after one full revolution. And for Mach number 10 to the minus 1, it actually looks very similar to what it looked like when we had it set up before we rotated it. But now if we go down to a Mach number 10 to the minus 2, after one full rotation, this Gresham vortex looks a bit blurred. And at Mach number 10 to the minus 3, it's completely gone. Dissipated away. All we see here is grid effect, so that's completely dominated by numerical artifacts now. Now, of course, if you look closely, this is a rather coarse resolution here, 40 by 40 cells only, but it demonstrates that if you have sort of a convective turbulent flow fields at the lower scales, you're always completely dominated by numerical dissipation if the Mach numbers get low. And this is, of course, something that we would like to avoid. Now the question is, what causes this problem of conventional hydro schemes when we go to low Mach numbers? Well, this can be explained in a phenomenological picture. So first think of how we model hydrodynamics numerically in the finite volume approach. So the idea here is that we discretize our conserved quantities, density for instance, in a sequence of computational cells. So this is how we discretize the continuous field in space. And in these cells, we assign the average quantity over that cell to the center of each cell. And then the update in the hydrodynamics is achieved by computing the fluxes of these conserved quantities over the cell interfaces in each time step. And the way this is done is that one actually takes the cell averages and somehow extrapolates towards the cell interfaces. And then, of course, one finds a jump in these conserved quantities. And a jump into conserved quantities plus a hyperbolic conservation law, the equations of hydrodynamics, gives you a Riemann problem. Now, the advantage with that is that for these Riemann problems, analytic solutions are known, and that's why we can actually solve for the fluxes, and this way update the hydrodynamics. And this is what the standard Godunov type solvers do. The problem with this is that in each time step we now construct initial conditions for calculating our fluxes that are inconsistent with the low Mach number problem, because in low Mach number flows we don't expect to have jumps in the conserved quantities. So the consequence in this phenomenological picture of that is that we will create artificial sound waves that are not resolved by our hydro solver, and this then leads to excessive dissipation at low Mach number. Another way to think about this in more mathematical and more formal way is the following. You ask the question, how do the partial differential equations of fluid dynamics scale if the Mach number goes asymptotically to 0? And you find certain solutions there. You can do this asymptotic analysis. And then the question is, you devise a discretized version of this and actually look into how this discretized version scales with a Mach number going to 0. And the question then is, does this recover the same solutions? Now, what we find actually, and this is the cause of the problem that I've shown, is that the numerical schemes usually don't recover the same solutions. And the reason for this is actually the way the flux function is discretized. So this is actually how the numerical flux usually looks like in row-type schemes or Godunov-type approaches. So usually this numerical flux consists of two components. One is the so-called physical flux, and then there's another term in here. That's the so-called numerical dissipation or upwind term. In the story with the Riemann solvers, this naturally arises from solving the Riemann problem, but you could also think about this as stabilizing the scheme, namely because the physical flux is unstable in an explicit time discretization, so therefore you need to introduce some numerical dissipation, and this is achieved by this additional term here. Now, the physical flux scales in a certain way when you go with the Mach numbers towards 0. The question is, does this upwind term, the numerical dissipations term, scale in the same way? And what actually we found in this analysis, together with mathematicians in Würzburg, and other people actually have done similar analysis, is that such an upwind term in the conventional way it is written down usually scales wrongly with the Mach number. You have some components in this term that diverge when the Mach number goes to 0. So that means if you go to low Mach numbers, this artificial dissipation term that you put in just for numerical reasons to stabilize your scheme will completely dominate the flow. And this is, of course, what you want to avoid. So we have thought about ways to prevent this, and there are different approaches in the literature, and my student Fabian Mitschek actually contributed one other possibility to this. So in the end, you modify this upwind dissipation term in a certain way to correct the scaling of that term with low Mach number. And this is actually very successful, as you can see here. So this is now a corrected scheme, and the Gresham vortex actually stays rather robust and undistorted, even if we go to low Mach numbers. And we've tested this down to Mach numbers of 10 to the minus 10. It should actually read here. Sorry for the aliasing of the projector. So this actually works very well to low Mach numbers. However, there are still some problems with this method if we couple this to gravity, and that's why we have, in addition to this kind of approach to deal with low Mach numbers, also implemented other schemes to deal with low Mach number flows into our 7-league hydro code. Another problem that we have when we actually want to simulate flows in stellar interiors is, as I said before, the star overall is still rather close to hydrostatic equilibrium. Now, hydrostatic equilibrium is something that is very, very difficult for dynamical codes to maintain for many dynamical timescales because of discretization errors. In particular, what is problematic here is that you discretize usually the fluid dynamic equations different from the gravity. And this mismatch actually then can easily distort hydrostatic equilibrium. So therefore, specific schemes are needed to compensate for this. These go under the name of well balancing, and some of these schemes have also been implemented in our code. In addition, we have a number of physics modules in the SLH code and a rather flexible grid geometry, and this then allows us to perform simulations of flows of low Mach numbers in stellar interiors. Well, one other requirement for trying to do 3D hydrodynamics in stars is, of course, these are very expensive simulations, so you need to make sure that the codes that you use for such tasks scale well to large supercomputers. And this actually has been tested in a scaling workshop on the predecessor of the current big machine in Jülich, and what we found there is that our code indeed scales to the entire machine up to 500,000 cores. All right, so applications of these methods are at the moment in our group to convective burning in stars, very similar to what Raphael talked about in his colloquium on January 7, for those of you who were there. So the basic questions that we want to address here is, what is the characteristics of the turbulent flow pattern that we find in these convective burning stages? And then, of course, we would like to characterize convective boundary mixing because this is of great importance for the fate of the star and for its evolution. And one other aspect that we actually recently looked into was the generation of astroseismic waves driven by convective motions in stellar interiors. Now the challenge with these simulations is that if we go to earlier and earlier burning stages, then the Mach numbers become lower and lower. So Raphael talked about convective carbon burning, which already has rather low Mach numbers, but you can still do that sort of with conventional hydro schemes. Now we tried actually to go to earlier burning stages, helium and hydrogen burning, then the Mach numbers become really low, and it seems advisable to use implicit low Mach number schemes for that. Now this is what a PhD student in our group, Leo Horst, did. So he actually took an initial 25 solar mass star that was calculated in a 1D stellar evolution code with MESA to helium shell burning, and then we mapped it to a 3D wedge, and this actually then was followed in our hydrodynamical simulations. Now from mixing length theory in the 1D stellar model, we would expect Mach numbers in this convective flow between 10 to the minus 4 and 10 to the minus 3, so this is pretty low. Now here is a cut through this 3D wedge in which we simulated the convective helium shell burning. On the left-hand side, you see a run that was done with a conventional hydro scheme. On the right-hand side, you see a run that was done with a low Mach number scheme. The spatial resolution is the same in both of these simulations, and you see that in the low Mach number scheme, we're able to resolve much finer structure in the convective flow field. However, I have to put in a disclaimer here. Although we were aiming with our schemes to really do the very low Mach numbers that we physically have, we still actually encounter problems if the Mach number falls much below 10 to the minus 3. So therefore, we still do some boosting of the nuclear energy generation rate to keep the Mach number above 10 to the minus 3, which is kind of artificial, but we hope that we actually can further develop our tools to really go down to Mach numbers 10 to the minus 4 or something that would be the physical Mach number here. All right, so this is actually how things look in 3D. The talk is called 3D view on stellar astrophysics. So this is the 3D wedge inside the star, and you see how the convective flow pattern evolves due to the energy input from helium burning. Now what you also see here is these little ripples on top of the convective burning zone, and this is actually what we are interested in as well. So this is the generation of astroseismic waves. Now, of course, astroseismic waves, as you probably know, is one way to look into stars to determine conditions in stellar interiors. And of course, they need some interpretation in order to draw conclusions on this. So it's important to do simulations of convective flow pattern in convective flows in stellar interiors and to see what signal they give in terms of astroseismic waves. Now, the way this is usually done is in a simplified approach to stellar hydrodynamics. So the codes that are used to do astroseismic wave simulations are so-called anelastic codes. They don't solve the force system of equations that I've shown in the beginning, but a modified version of it. And this modified version does not allow for sound waves, so this makes the treatment numerically much more efficient, but of course it also precludes the possibility to follow P modes. So there are two different kinds of astroseismic waves, so-called P modes and G modes, depending on which is the restoring force in this hydrodynamic wave. For P modes as the pressure, like in ordinary sound waves. For G modes, these so-called gravity waves, not to be confused with gravitational waves. In gravity waves, the restoring force is buoyancy. And anelastic codes can only recover G modes, so therefore in our code, where we actually discretize the full set of equations, the full compressible order equations, the hope is that we actually then can also recover the P modes correctly. But one thing that we want to make sure is that we also, with the G modes, do the right thing with our code. So are we actually able to follow the propagation of G modes correctly, of gravity waves correctly? And in order to test this, Leo has set up this wave package of gravity waves, and we follow its propagation here on top with our low Mach number scheme and on the bottom with a conventional hydro scheme. The Mach number of the propagation speed of that wave package is on the order of 10 to minus 3, so this is a low Mach number problem. And what we see consequently is that if we actually treat this with our low Mach number approaches, then the dissipation of the amplitude of that wave package is still there, but it's much less than the dissipation of the amplitude that we observe for the conventional scheme. The other interesting thing is that our low Mach number scheme seems to reproduce the propagation velocity, so the dashed lines here is the expectations, the theoretical expectations. So the propagation is actually rather well reproduced with the low Mach number scheme, whereas the conventional codes overestimate the propagation speed. Now, therefore, we then performed simulations of the generation of astroseismic waves due to convective burning in a star. And as an example, we took a 3 solar mass star with core hydrogen burning. And this is what it looks like. So this is actually the core where hydrogen burning drives convective motions. And the outer layers, you see these wave patterns. So what's color-coded here is the velocity, the lateral velocity. And these waves are the ones we're interested in. And we can actually, from this, extract spectra of these astroseismic waves that's shown here. I don't want to go into much detail about this here, but just mention that actually, as expected with our compressible hydros approaches, we are able to recover G modes and P modes, and we find generally a rather good match to observations and also to theoretical predictions. Now, goals in this work is to determine whether we find mixed modes. So there are some modes predicted that have a mixed character between P and G modes. We look for nonlinear effects and potential angular momentum transport due to astroseismic waves. Okay, conclusions on this first example. I hope that I could actually convince you that time-implicit, low Mach number methods are promising, but they are still a rather rocky road towards progress in stellar hydrodynamics, and we hope that we, with this approach, can contribute to developing the next generation of stellar models. Second example, now we diverge a little bit more from hydrostatic equilibrium, and this is supernova explosions. So here, we not only abolish the assumption of spherical symmetry, but also go far away from hydrostatic equilibrium. Now, I will talk here about thermonuclear supernova explosion. This actually has a little bit to do with binarity, but I will not focus too much on this here. Now, the fundamental problem in simulating thermonuclear supernova explosions as a model for type 1a supernovae is the infamous progenitor problem. And this is actually that we so far have no convincing observation of a progenitor system out of which a thermonuclear supernova arises. And in terms of modeling, this is a very fundamental problem because of the nature of the equations that we're trying to solve. So this is again the Euler equations that I've shown at the beginning. These are hyperbolic partial differential equations. They pose initial value problems. You can solve them numerically, but only if you know the initial conditions. And this is what we don't know for type 1a supernovae because we don't have good observations. And even if we had observations, we still wouldn't know how this star really ignites and at which conditions it ignites the thermonuclear burning. Now, there are different progenitor channels discussed in the community. So one idea is that, well, it's always assumed that a thermonuclear supernova explosion explaining type 1a supernovae is the explosion of a of a carbon-oxygen white dwarf star. The question is how this white dwarf star reaches explosive conditions. And one possibility is that it actually ignites burning when it comes close to the limit of its stability, the famous Chandrasekhar mass. And this can be, for instance, achieved by accreting material from a normal non-degenerate companion star until the white dwarf reaches the Chandrasekhar limit, and then it triggers an explosion, which is rather natural because coming close to the Chandrasekhar mass, the density in the core grows strongly so that the ignition of carbon burning is unavoidable. Alternatives have been also suggested. One famous alternative is the merger of two white dwarfs, and this is then in the community slang called the double degenerate progenitor scenario. Now, our problem is that we don't know how the explosion starts, what triggers the explosion, and how the white dwarf at the onset of the explosion looks like, so we have to take a guess here. So therefore, our approach is then taking this gas and modeling the explosion stage as precise as we can, and follow the nuclear synthesis in this explosion so that we are able to predict a ejector structure that can be used for radiative transfer. And our colleagues in Belfast, Stuart Zim with his group, and also Markus Kromer, who was here as a Gliese fellow, they then used their radiative transfer codes to derive synthetic observables, synthetic light curves and spectra from our models, so that we can directly compare to observations. Now, the hope with this is that this comparison will tell us about the validity of the assumptions that we made on the initial structure of the white dwarf star and on details of the explosion mechanism. But of course, in order to make this work, we have to make sure that we don't introduce too many tunable parameters when modeling the explosion stage, because only then we are predictive enough. So we have to avoid tunable parameters. And this is actually why we have to go multi-D when modeling these supernova explosions. Now, as many of you may be aware of, there are also one-dimensional explosion simulations of type 1a supernovae that have been very successful in reproducing observables. And the most famous example is certainly the W7 model of Ken Nomoto. So here, the most important physical parameter, namely the propagation velocity of the thermonuclear combustion wave, was parameterized and taken as a few tunable parameter. And by this tuning the parameters, actually a good match with observations was achieved. And this is all nice, and you can actually use that to interpret observations. The question then is, can you rely on such models for other purposes? For instance, using them as input for galactic chemical evolution studies. And I would argue that this is rather dangerous because the assumption of a spherically symmetric incineration of a white dwarf star is rather artificial. So the basic picture of these 1D type 1a supernova models looks like here. So we have a white dwarf star that is ignited in the center, and then the combustion wave propagates outward, spherically symmetric, with a tunable, free, adjustable propagation speed. So this is one of the problems. The other problem is that in this spherically symmetric combustion, the ashes that you produce in the burning stay at rather high densities for very long because they always stay in the center in the spherically symmetric geometry, and therefore they have a lot of time to neutronize by electron captures. And this is a known problem of the one-dimensional type 1a supernova models. They overproduce highly neutron-rich iron group elements and compared to solar abundances, and this has been a long-standing problem. Now, therefore, we want to go to multidimensional simulations. There's a number of reasons for doing this: ignition, potential interaction with companion star. All these are three-dimensional effects. Here I will focus on modeling the flame propagation. Now, the flame propagation model is, again, a spatial scale problem, and this is because of the high temperature sensitivity of the nuclear burning. So we want to actually thermonuclearly burn carbon-oxygen material. So this starts out with carbon-carbon fusion, and carbon-carbon fusion is a heavy ion reaction. We have to overcome the Coulomb barrier, and therefore we have an extreme temperature sensitivity of the reaction rate. So in the regime we are looking at here, the reaction rate scales with the 20th power of temperature. So this means that burning is always confined to the thin layer where the temperature is highest. And therefore these combustion waves inside white dwarf stars are actually very thin, so they have an internal width of only millimeters to centimeters. And this is, of course, tiny compared to the dimensions of a white dwarf star with a radius of thousands of kilometers. So therefore, it's well justified to describe these flames or combustion waves in a so-called discontinuity approximation. So we just model them as sharp discontinuities separating the fuel from the ash material. And if you do that, then together with the equations of hydrodynamics, you find jump conditions. And these jump conditions then distinguish between two fundamentally different modes of flame propagation. And one mode is called deflagration. So here we have a subsonic progression of the thermonuclear combustion wave, and the alternative to this is a supersonic detonation. Now these are actually also rather distinct in their physical nature. In a deflagration, the flame propagates due to heat conduction, in our case of the degenerate electron gas, and this is actually what propagates the reaction, the burning. And that's why it's subsonic. And in detonations, the burning is driven forward by the propagation of shock waves, and this is why it is a supersonic propagation mode of the combustion wave. Now I will now focus on the subsonic deflagration mode, because this is actually what was used as sort of the underlying picture of the W7 model and other one-dimensional type 1a supernova models, where the flame propagated from the center outwards in a spherical way. But this is not what we would expect physically, because when we actually start burning at the center of the star and the flame propagates outwards, then the flame actually leaves behind light and hot ashes, and in front of the flame the dense and cold fuel material. In the ashes, the degeneracy of the material is partially lifted. So this is why we find inverse density stratification in the gravitational field of the star, and this of course leads to buoyancy instabilities, and the Rayleigh-Taylor instability in its nonlinear stage leads to these mushroom-shaped bubbles of material that rise to now this, first of all, means that these hot ashes don't stay at the center for very long high density, but they quickly move out to low density regions, and therefore we have much less electron captures, and therefore the material neutralizes much less. Now the second implication is that at the edges of those bubbles, shear flows are expected to emerge, and this is actually where the flame is located. And these shear flows have Reynolds numbers up to something like 10 to the 14. So these are huge Reynolds numbers, and this tells us that turbulent eddies will be generated and a strong turbulent cascade is expected to form. Now the consequence of this is that the flame will start to interact with turbulent eddies of various sizes, and this actually allows us to fix the propagation speed of the flame to a physical value, although we still model the flame as a sharp discontinuity and don't resolve its internal structure. But what we actually find in this situation is that the flame is completely driven by turbulence. Why is this? Well, this is actually because we are burning in a so-called flamelet regime of turbulent combustion, and here the idea is that although turbulent eddies still are not strong enough to penetrate the internal structure of the flame, and it still locally propagates with its laminar speed given by microphysical transport processes, on larger scales, turbulent eddies will actually wrinkle and corrugate the flame surface area. And this, of course, then greatly enhances the flame surface area, and this leads to a strong acceleration of the flame. So this is actually why car engines run. So you do the same thing here, turbulent combustion. Now, what's the problem with that? Well, the problem with that is, of course, that we cannot, in numerical simulations, recover turbulence with Reynolds numbers of 10 to the 14. So therefore, our model flames will always be too smooth, and in order to compensate for the lag in flame surface area, we therefore have to ascribe an increased effective turbulent velocity to that flame. And the question is, what should be this effective turbulent burning velocity? And luckily, there's theory about this already dating back to the 1940s, when Darmköhler suggested that this turbulent propagation velocity of the flame at the cutoff scale should be just proportional to the turbulent velocity fluctuations on that scale. And this actually has been confirmed since then in a large number of experiments. So this asks to determine the turbulent velocity fluctuations, and then we know the propagation speed of and how we do that, we use actually a large eddy simulation type of approach with a turbulent subgrid scale model for determining the flame propagation speed, and in this way we can then actually parameter-free model the flame propagation through such a white dwarf star and put this into our modeling pipeline. Now this is something that we would like to test on explosions scenarios with a Chandrasekhar mass white dwarf, because one would expect that a Chandrasekhar mass white dwarf burns initially, at least, in this subsonic deflagration regime. Why is this? Well, this is actually because Chandrasekhar mass white dwarfs are rather compact objects, and this is shown here. So this plot shows the density over enclosed mass. And this is a Chandrasekhar mass white dwarf in hydrostatic equilibrium. What you see here is that most of its material up to here, up to almost 1.4 solar masses, is actually at densities above 10 to the 7 grams per cubic centimeters. And if such material is burned, we arrive at nuclear statistical equilibrium, and in the end this produces iron group elements, in particular nickel 56. Nickel 56 is radioactively unstable, decays and makes the supernova bright. Typically we have to produce half a solar mass of nickel 56 to explain a normally bright type 1a supernova. But in this model, if we actually burn the white dwarf in hydrostatic equilibrium, then we would actually produce 1.4 solar masses of nickel 56. And this is, of course, inconsistent with the observations, also because in spectra of type 1a supernovae, we find indications that there's lots of intermediate mass elements present in the ejecta, such as silicon, sulfur, oxygen, and so on. This characterizes the spectra of type 1a supernovae. So that means that we cannot burn this white dwarf in hydrostatic equilibrium, which we would do in a supersonic detonation wave. So therefore, only a deflagration works, because then in the subsonic burning mode, the star can pre-expand before it actually gets incinerated. And this is actually what we follow in our simulations. So this is a Chandrasekhar mass carbon oxygen white dwarf ignited in the center as a deflagration. A deflagration flame propagates outwards, is subject to buoyancy instabilities. You see these Rayleigh-Taylor mushroom-shaped bubbles. It accelerates due to the interaction with turbulence, and in the end we get an explosion. Now, the strength of the explosion, the outcome of some such simulations, of course, as expected from the nature of the system of equations that we solve here, depends on the initial conditions. And the most important initial parameter here is the way the flame gets ignited. And unfortunately, this is still rather uncertain from simulations. So we have taken this here as a parameter and ignited a Chandrasekhar mass white dwarf near its center in different number of ignition sparks that we distributed randomly around the center. And what we find here is that the outcome, the strength of the explosion is strongly sensitive to the number of ignition sparks that we choose. So this here is the ejected mass for models that are ignited with different numbers of ignition sparks, 1, 3, 5, up to a few hundred or 1,000 even. And what you see here is that only if we ignite in, say, hundreds to thousands of ignition sparks, then we actually completely unbind the entire white dwarf star. So this completely disrupts the 1.4 solar mass Chandrasekhar mass white dwarf. If we ignite in fewer ignition sparks, then we have an incomplete disruption of the star. Only like 0.4 solar masses of material get ejected, and we are left with a bound remnant of about 1 solar mass. The other quantity that's plotted here in red is the nickel 56 mass that's produced here. As you see, in all of these simulations, it stays below the canonical value of half a solar mass that you need for a normally bright type 1a supernova. So what do we expect from such simulations is actually not normal type 1a supernovae, but peculiar faint events. In particular, one can look into this example here with 5 ignition sparks. We followed this in the hydrodynamical explosion simulations, and then our colleagues derived synthetic observables, light curves, and spectra from this. They don't look like normal type 1a supernovae, but actually they reproduce an observed subclass of supernovae rather well, the so-called O2CX-like objects. And therefore, these can potentially be associated to deflagrations in Chandrasekhar mass white dwarfs. Now recently there has been the suggestion that these are actually only sort of the brighter end of a more extended sub-class of type 1a supernovae that have been called type 1ax supernovae. So this is unfortunately not well visible here. This is the brightness of the supernova over decline rate. Here are the normal type 1a supernova with the famous Phillips relation that's used to calibrate these objects as distance indicators in cosmology. Type 1ax supernovae are much fainter and form a distinct subclass. Now, the objects that we were able to simulate so far are the brighter end of this subclass. The question now is, can our models also reproduce the fainter ones? And this is something that my PhD student Florian Lach is currently working on. Now, these are peculiar subclasses of type 1a supernovae. The question is, how can we actually reproduce normal type 1a supernovae, the normally bright type 1a supernovae? And there have been different suggestions, and we have actually also with our group followed different scenarios. Here I will actually mention one particular scenario in which a subchandrasekhar mass white dwarf is detonated. This is possible because subchandrasekhar mass white dwarfs are much less compact. As you see, a lot of their material is below the density threshold of 10 to the 7 grams per cubic centimeter, so we can overrun it with a detonation and still produce intermediate mass elements. The question then, however, is how do we trigger a detonation in a subchandrasekhar mass white dwarf? And there have been different suggestions in the literature, collisions of 2 white dwarfs, the merger of 2 white dwarfs, or the so-called double detonation model, and this is something that we have been recently looking into. So the idea here is that a carbon-oxygen white dwarf that's below the Chandrasekhar mass accretes material, helium-rich material from a companion star, and the helium-rich material piles up at the surface, and then when it gets massive enough due to compressional heating, ignites a detonation. And this detonation wave then sweeps around the core and drives a shock wave into the carbon-oxygen core. And the question is whether then it ignites a secondary detonation in this carbon-oxygen core to trigger something that might look like a type 1a supernova. And this is something that Sabrina Grono in our group actually currently is simulating. Here is one of her recent simulations. You see how the helium shell detonation sweeps around the carbon-oxygen core, and it converges on the far side and compresses material there so much that a detonation actually in the carbon-oxygen material then triggers, and then a secondary detonation gives rise to a disruption of this star. The question here is whether such models can reproduce spectra of normal type 1a supernovae, because a known problem here is that in the outer parts of the ejecta we have the material that has been produced in the initial detonation of the helium shell, and this is inconsistent with observations. So the question is, can this be hidden? Is radiation transfer precise enough to make the right predictions about that? And this is something that we currently are exploring. Now, conclusions on this part. I hope that I could show you that our explosion pipeline is a valuable tool to test progenitor scenarios of type 1a supernovae. It needs predictive power in order to do so, and this is achieved by consistent multidimensional modeling. And we are currently, with collaborators in China and Japan, also extending to other kinds of observables the interaction of a supernova blast wave with a companion star and consequences for polarization in the spectra, and also the formation of the supernova ambient. Okay, third and final example, binary stellar systems. Now here, we not only remove the assumption of spherical symmetry and hydrostatic equilibrium, but also that stars are single objects. So, as you may know, interaction in closed binary system is one of the greatest uncertainties for making predictions of the occurrence rate for type 1a supernovae, neutron star mergers, X-ray binaries, and so on. This actually is fundamental for forming compact binaries. And the phase that we are in particular interested in is the so-called common envelope phase. So the idea here is that you have a closed binary system in which the more massive companion evolves into the giant phase first, so that it overgrows its Roche lobe, and then we have mass transfer to the companion star. This mass transfer may be unstable, so that the companion star is finally completely engulfed in the envelope of the primary star. And then these two stellar cores start to orbit each other inside this common envelope. The idea is that by tidal friction, they transfer some of their orbital energy onto the envelope, and that the envelope finally is ejected, so that we are left with a closed binary system that's close enough to trigger supernovae, neutron star mergers, and so on. The problem, of course, is that this is an inherently multidimensional process. It cannot be consistently captured in 1D parametrizations, so therefore all the predictions that we have from population synthesis on merger rates of neutron stars, for instance, have large uncertainties because of this common envelope phase. Now, simulating the common envelope phase is actually difficult in two respects. One, again, is the spatial scale problem, because inside a giant envelope we have a rather small and dense core, and the companion star may also be rather small and compact, so it's hard to resolve the scales of these stars. At the same time, the dense cores actually mean that in explicit time discretizations, we have to take very small time steps inside these cores, but we are ultimately not interested in resolving the physics inside the cores, but in the envelope. So therefore, what one usually does is one usually replaces these stellar cores by gravitationally only interacting particles. And this is something that is actually easily possible with the AREPO code that was designed for cosmology here in Heidelberg by Volker Springel. It actually features gravity-only particles that were used to represent dark matter particles, and we actually have used them and use them for representing stellar cores. The question is then, how can we stably construct a stellar envelope around this? This is not trivial, but has been solved by Sebastian Ullmann in his PhD thesis. Now, another problem with common envelope simulations is that this is inherently a Lagrangian kind of problem, because you want to follow the orbiting of two stars for long timescales, for many orbits, and with a traditional fixed mesh hydrodynamics codes, you would run into problems with angular momentum conservation. This is much better in Lagrangian codes. SPH codes, smooth particle hydrodynamics codes, have been used for common envelope simulations, but these actually have the problems that they don't resolve hydrodynamical instabilities in the envelopes very well. So therefore, the moving mesh code, a repo, which combines the advantages of a mesh code with that of an SPH code, seems to be an ideal tool to simulate common envelope evolution. And Sebastian Ullmann, my former PhD student, has done so. So he has set up common envelope interaction between a 2 solar mass red giant with a 1 solar mass companion star. And this is what it looks like. So this is the companion star diving into the envelope of the giant primary. Then they orbit each other. A spiral shockwave forms. And what one also sees here is that after a while, a strong hydrodynamical instability develops in the envelope and leads to mixing of the material. So this is something that had been expected for a long time, but never really been resolved in hydrodynamical simulations, because in SPH simulations, you actually don't reach the precision to see these hydrodynamical instabilities. Now, this is interesting, but it doesn't solve the fundamental problem that many people have when simulating common envelope evolution. And the problem with common envelope simulations is that most of the simulations that are on the market are not able to explain the envelope ejection. And this is actually also what happens in our simulation. We see that the distance between the two cores approaches each other in the first few orbits, but then this saturates, and we eject only something like 8 to 10% of the envelope, but then the evolution stalls. And the reason for this is that first, the orbital energy is actually transferred to the envelope expands, and then there's little material left around the cores, so it's harder and harder to really transfer angular orbital energy to the envelope. So therefore, there must be a different mechanism that helps envelope ejection. And people have speculated about this, and one suggestion was maybe it's the generation of strong magnetic fields that helps ejecting the envelope. Now, this is something that we can test because the repo is actually an MHD code, and so we were able to perform the first MHD simulations of common envelope evolution, again with the same setup. And what we see is indeed a very strong amplification of the magnetic field in the common envelope evolution. In the first orbit, the field strength grows considerably. Then we have a slower growth phase, slow amplification phase, and finally a saturation. Now what we find is actually that the amplification of the magnetic field is not, as people previously thought, because of a large-scale dynamo inside the common envelope, but it's rather inside the accretion stream that forms around the companion star. And the mechanism that leads to the strong amplification of the magnetic field is the magnetorotational instability that Jim Stone talked about in his colloquium before Christmas. Now, what we find then is actually an amplification of the magnetic field from a seed field of, say, 10 to the minus 6 Gauss or so, it doesn't really matter what we put there in there particularly, to something on the order of 10 to 100 kilogauss, so a strong amplification of the magnetic field. But still, it's not strong enough to be dynamically relevant, so it's not magnetic fields that actually drive common envelope ejection, although they may help to shape the planetary nebulae that may actually arise from such systems. So therefore, we tested yet another effect that had been suggested, and other groups have actually also looked into this, and this is recombination energy. So one energy source that you can potentially also tap in common envelope evolution is the ionization of the material. So the envelope of the star is initially ionized. When it expands in the common envelope evolution, the outer parts drop below the ionization threshold in temperature, and then the ionized regions recombine and release energy. And this may help to eject the envelope, and indeed what we see is, so this is the ejected envelope of mass over total mass as a function of time. Here we have pure hydro simulations without taking into account the ionization energy. We eject only very little of the envelope material, but if we actually take into account the recombination energy as it is released in this yellow and blue lines here, then we see that we finally get a boost of the envelope ejection so that we reach almost a complete ejection of the envelope of the giant star. So this can potentially solve the problem of envelope ejection, but it depends on the critical point of whether we are really able to use all the recombination energy as it is released. And this is not clear because recombination energy is actually released in outer, rather thin layers of the envelope, where the optical depth may be not very high anymore. So it is also possible that part of that energy just gets radiated away instead of being thermalized and contributing to the kinetic energy. So this is something that we're currently exploring by putting in radiation transfer into our simulations. I will skip this slide here. Final point I wanted to make is we have also recently, with our Gliese fellow here in Heidelberg, applied those methods to simulating stellar mergers. So the idea that Fabian Schneider actually brought in was the question of why we observe about 10% of all massive stars featuring strong magnetic fields. The origin of this is mysterious. We know that low-mass stars like our Sun have magnetic fields, but they have a convective envelope where you actually can drive a dynamo and generate dynamically the magnetic field. The question is, where do these massive stars that have a stable non-convective outer envelope, where do they get their magnetic fields from? An example for such a star is Tau Scorpii, which is a 17 solar mass star. And the interesting thing here is that this star actually also appears to be young compared to its neighbors, so it's a blue straggler. Now, therefore, the hypothesis is that such stars could arise from mergers of two close stars, because this may, first of all, generate strong magnetic fields, and also merging of stars is known to lead to rejuvenation, so these may actually appear then in the end as blue stragglers. And incidentally, it's also from observation constraints assumed that about 10% of all massive stars are products of mergers. Now this is a speculation, has not been tested, and therefore Fabian and my student Sebastian Ullmann went on and set up such a merger simulation between a 9 and an 8 solar mass main sequence star to perhaps reproduce something like Tau Scorpii. This is how the simulation looks like. These are the two merging main sequence stars. In this case, of course, we don't have to replace any stellar cores by point particles, but we can resolve the entire stellar structure. And this is actually now the merger phase. And after this merger, we actually then terminate this hydrosimulation when a 14 solar mass core has formed that's surrounded by a 3 solar mass torus that's surrounding this configuration. Now the question is, do we see a strong amplification of the magnetic field? And indeed, this is actually what we find. We find an amplification of the magnetic field by many, many orders of magnitude. Again, like in the common envelope simulation, this happens due to the magnetorotational instability in shear layers around the merging stars. And in the end, what we find from this simulation is actually a magnetic field that's strong enough to explain the observed magnetic mass of stars. So Fabian has actually followed the further evolution by mapping the structure back to a 1D simulation and following the evolution in 1D in the stellar evolution called MESA. And such stars may ultimately be the progenitors of magnetars. Okay, so conclusion of the last part of the talk. Moving mesh hydro is a powerful tool to follow the multi-D simulation of binary stellar interaction, common envelope phases, stellar mergers, and also measures of compact objects, of course, target for such approaches. Okay, so this actually is already the end of my talk. I don't have actually conclusions here, but what we thought would be something that actually sort of fits to the title of my talk, the 3D view on stellar astrophysics, Well, what I've shown to you here was at best movies of simulations that were done in 3D, but it was not really a 3D view. Well, we have in principle the capability for immersive virtual reality, where you can really take a look into the 3D structure of our simulations. And we were hoping to be able to set this up before the colloquium. It didn't quite actually work, but maybe Melvin, you can actually sort of, maybe you can actually sort of try to get it running now. So we will try our best to get this running, and you can actually on your way out test it and take a real look into the 3D stellar hydro aspects. Thank you very much.
So, thank you, Fritz, for this fascinating journey through stars' interiors and how they blow up. Are there questions? Yes.
Concerning the supernovae, when you have nuclear reactions in a turbulent medium and the reactions depend very steeply on temperature, do you not also need the temperature in very high spatial resolution?
Yes, so the regime that we actually encounter in Type 1a supernovae is the so-called flame-lit regime, and the idea there is that you have strong turbulence, but not at the scales of the internal structure of the flame. And you can actually motivate this by the notion of a certain cutoff scale, the so-called Gibson scale, and this is the length scale on which the flame propagates faster through the turbulent eddies than they can actually distort it. Because inside the turbulent cascade go into smaller and smaller scales, the turbulent velocities will decrease in turbulent cascade, but you have a certain laminar burning speed of the flame. And at some point, the flame will just rush over the turbulent eddies without noticing them. And the question is at which scale this happens. And if this scale is much, much larger than the internal width of the flame, then the internal width of the flame in nuclear reaction will not be distorted by turbulence, because turbulence cannot penetrate the internal structure of the flames. And this is actually what applies to most parts of the supernova explosion. Maybe in the very late phases this changes when the star has expanded and the density has become low, then the burning speed of the flame is low enough so that actually turbulence can interact with the actual burning zone inside the flame. And this actually is the regime where people have speculated about a transition of the flame propagation mode from subsonic deflagration to supersonic detonation. So then you really change the way the flame propagates. But this is all speculation, and it's very hard to simulate.
Another question? While you're thinking of questions, let me ask one. What is the reason why you can have multiple ignition points? Because I would imagine that once one ignition goes, it's much faster than the change of conditions elsewhere to ignite it.
Yes, so this is probably true. I mean, the conditions under which you ignite this is actually also turbulent burning, because you have convective carbon burning before the flame really ignites until you actually reach thermonuclear runaway. And so in principle, it's possible to think of multiple ignition sparks in this turbulent field, because you're very close to thermonuclear runaway, and you may think it happens in many points, but as you say, the timescale argument speaks against it, and it may well be that the first spot where this is achieved dominates everything. And this is actually what simulations of that regime also show. The problem then still is, how do you actually sort of initiate this in a multi-D simulation of the explosion itself? And if we actually would take just one single bubble somewhere, this is not a well-defined numerical setup. We have to put in some perturbations, because otherwise we have never a chance to reach numerical convergence if we refine this, because then everything, how the radiational instabilities develop, so will be completely dominated by the initial seeds due to discretization errors. So this is one of the reasons why we have multiple ignition sparks, and the other is just sort of as a toy model to see what actually the deciding parameters are and how strong this impact would be when we change the strength of the deflagration.
So, if there are no further questions, are we ready yet for the 3D simulation, 3D visualization, or a couple of minutes? So don't run away.
Yeah.
And could you show?
I will try to do that. So
yes. So in the meanwhile,
okay.
Yes, thank you very much. So before we thank our speaker, Fritz, again, the next week's colloquium will be Carlos Frank. Definite test of the cold dark matter model, no ifs or buts, so that's fascinating. But it's also now time to thank for another fascinating talk, namely the talk today. So let's thank Fritz for his nice talk.